Hello all, welcome to part 6 of the Buffer Overflow Primer video series. In this video, we will look at how to exploit a vulnerable program using the shellcode which we created in the previous video. So this is an example of a vulnerable program. Very simple program where we have a buffer of 80 bytes and there is a user supplied input which is stored in argv1, and then we have the vulnerable function string copy which simply copies argv1 into the buffer without really checking for the size of argv1 and the size of the buffer. So very typical kind of a vulnerable program where there is no bounds checking happening. So how would we go about exploiting such a program? First, let's go about looking at the stack of this vulnerable program exploit.me.c. So once we are inside the main function, how would the stack for exploit.me.c look like? Now we've arranged this from low memory to high memory. And if you remember in the assembly language primer, as we talked about, in the lowest memory we would have the buffer local variable which is of size 80 bytes. Then we would have the stored frame pointer, right, EBP, which is of 4 bytes, and then finally the return value from main, which is once again 4 bytes. Now if you remember, as we've seen in previous videos, the return value from main is nothing but points to libc_start_main, right? So this is how the stack view looks like. Now, how do we exploit this program? So let's understand this a bit better. So what we have to do is somehow after the program returns from main and pops this return value into EIP, we need to be able to take control of this return value and then execute our own code, which probably creates a shell, right? So how do we do that? So we have to somehow push in our shell code and have it overlaid onto this memory location, as well as change the return value appropriately. So let's say using argv1, we go ahead, push the shell code, which is of 24 bytes. And then we go ahead, pad it with an additional 60 bytes. It does not really matter what this is, apart from the fact that it should not be null. And then we have our pointer, which actually points to the shellcode which needs to be executed, and that is 4 bytes. Now if you look at it, I've mapped it exactly to the previous stack layout. So basically what needs to happen is that in place of buffer and EBP together, we would basically have our shellcode and some padding wherever required, depending on the size of the shellcode. And then on the return address, which is stored on the stack, we need to override that with our own pointer to the shellcode, right? So this is what we have to do. So how do we go about doing this? And this is where we look at the concept of hacku.c, which is the program which is going to go ahead and compromise exploit.me.c. So the first thing we need to do is create a buffer which is going to set an environment variable, right? Let's name the buffer egg. Let's name the environment variable egg. And then after that, this egg is going to contain, of course, the 24 bytes of shell code which we talked about in the previous slide. Then it is going to go ahead and contain 60 bytes of padding, which we could just go ahead and put a nope instruction there, which is 0x90. Doesn't really matter, in this case, whether it's nope or whether it is just an illegal instruction, till it is a non-null value. Then we put a pointer back to our shell code, which is going to be 4 bytes in size. And then finally, a null of 4 additional bytes. Now the main challenge is actually going to be to find the location of the shellcode in the process so that we can set the pointer value appropriately. right? So let's actually go back and recapitulate a little bit about what all we spoke. So basically, if you look at it, what we need to do is, this is the stack layout of the program. We have the buffer 80 bytes, we have the frame pointer EBP 4 bytes, and the return value 4 bytes. Currently, the return value points to libc underscore start main, right? We need to make it point to our shell code. But where do we store our shell code? We need to store our shell code somewhere in this buffer, which we are going to overwrite, right? So what we do is, in argv1, we are going to have a shell code, then some amount of padding depending on the size of the shell code. And then finally, we will also have the pointer, which is going to overwrite the return address. And this pointer points back to our shell code. So this entire stretch of 24 plus 60 plus 4, which is 92 bytes, 88 bytes, right, is what is going to be our value of argv1, which is going to overwrite the buffer on the stack, right? Now coming back, how do we do that? Well, what we are going to do is go ahead and create an environment variable, which we are going to inject into the program's environment. And that environment variable is going to be called an egg. And it will contain the shell code, the padding, the return address pointer, and null. This is 4 bytes, could as well be a single byte. Doesn't really matter, right? So now let's move on to the demo of exploit me and hack you. And this is something which we'll cover in the next video. So please leave behind your comments for this video and let me know what you liked or disliked. That's all for this video. Thank you.